So I'm Francesco Zuccari. I'm the Global Support and Training Manager for GMX. Today I will run this webinar dedicated to the UHF radio communications applied to the survey world. With my pleasure, I would like to introduce on my right side to Marko Saarni from Satel. Welcome, Marko.
Hello, Francesco. Good to hear from you and everybody online.
So thanks to participate to this webinar, Marko. Marko is the OEM customer sales manager in Satel. Is it right, Marko?
Yes, that's correct. So I have been working with a company for last 15 years. Started as a technical support engineer, and slowly but surely turned to a little bit of product management side, and nowadays I work as a sales manager for mainly for GNSS customers, but for other OEMs too.
So I know you now since more than 10 years, Marko. In my particular case, is sometimes in my life jacket in some of the cases where I had some luck in the UHF communications, and Marko helped me really a lot in the past and even today. For this reason, it's with my pleasure that I invited Marko to explain us some of the arguments of this webinar. So in survey, and in particular to the GNSS applications, the communication between base station and rover is one of the most important topics. Today, we can use different technologies to connect a rover to a base, to a reference base. We can use the GSM modem, for example, that today is mainly used to connect to a GNSS reference network, and only in particular cases to connect point-to-point the two receivers. So, in both of these cases, we depend by some imperative conditions. So the presence of the GNSS reference network in our job site, in our working area, and for sure, the presence of a GSM network provider. What makes the surveyors really independent from this problem is the UHF radio device. Satel is one of the biggest and probably the best UHF radio device producer in the world, and for this reason, Hexagon and for GMX is the choice for our device. So the technology today helps us to make the usage of the UHF radio really simple. And even if we have some knowledge lacks, we can come back office with our job done in 95% of the cases. But in the rest of the cases, to know something in deep can help us to achieve the last 5% and make our life easier. So Marko today will help us to clarify some basic concept and to achieve that 5%. Marko?
Yes, thank you very much. That's a very brief introduction, and definitely it's my pleasure to have this opportunity to tell you a little bit about Satel, and also I hope I can share some practical tips and topics with you. Let's say to cover most common use cases that we already received some questions from the GMX support team.
Good.
I guess Francesco, my screen is visible properly. The first slide. Yes.
Yeah.
Okay. So just a quick introduction regarding the company of Satel. First of all, for today in this webinar, I will cover the following topics more or less quickly or briefly. Let's try to meet the schedule which has been provided. A little introduction on Satel as a company and how we operate, how the radio modem operates, how can we detect ourselves under interference if interference is affecting our performance. Very quick vision we'll take for identifying the main factors for achieving the range or coverage while operating out on the field, and then a couple of comments about the base station solution, and then finally there was a request regarding the base station battery capacity. So just let's have a quick look on the factors that help us to improve the operating time and efficiency when we are out on the field.
That's great, Marko.
So what we always want everybody to know is that Satel is the company located in Finland. So everything we do when we operate, where we cooperate with our customers is done in Finland. So in one building in Salo, we have a manufacturing site, R&D team, and also sales and marketing. And there are 75 people who are working in Satel today. Basically, we are a global privately held company focusing on these private data radios and radio connectivity solutions. So we do not, let's say, compete with others than maybe other technologies like Francesco mentioned, GSM or mobile networks and some other private data radio manufacturers. We export more than 90% of our products. So basically, Finland we cover by ourselves as a local distributor, but we have a distributor network covering more than 100 countries in operating out there, so to speak. We ship approximately 40,000 radios every year, and basically operate on all continents, literally all continents, as Antarctic as well has some radios in there. And basically our product range, we have certain variables for different frequency ranges, starting from VHF up to sub-gigahertz 900 megahertz radios, and also 2.4 gigahertz solutions. But main focus in our product range is this sub-gigahertz area. And our aim with the companies like Hexagon and Geomax is that we are the connectivity partner for our customers. So we don't necessarily just sell the goods out, but we also have a high expertise support available. Also in designing phase, we can consult our customers in question. Main target is that we provide private radio solutions which offer the reliable and cost-effective long-term solutions for our customers. Comparing to certain other technologies, 2G, 3G, 4G, and so on, our technology has has been there for quite some time, and still today the compatibility to original products that are operating out in the field can be provided.
Good.
Mainly in this industry, we are in GNSS industry, we are known among land surveying, precision farming, and machine control application areas. But we are much more. So Satel equipment you can find also from fleet management systems, smart grid systems, security, telemetry, and utilities. Actually, our very beginning where we started from was in water utilities, when we decided 30 years ago, and we established the first monitoring and controlling networks which were operating over radio links in water treatment company. But today our aim is to focus on this GNSS and surveying solutions. Therefore, I have picked up the list of products just to show you the product range we can offer. From little modules nowadays all the way to high power base station or repeater station radios, and several kinds of variants in between. The R4 module, which we have here, is currently the unit which has been integrated inside of Zenit 40, for example, and the high power radio solution.
Yeah.
High power radio solutions are or have been there for quite some time. And then we have some other alternatives with housings, with IP69K protected housing, which is used, for example, in machine control applications, and then a standard Satelline Easy product, which in GNSS industry has been in use in machine cabins sometimes, and on the other hand, same product might be operating there close to your home in electricity distribution network or in water treatment systems. So
the market,
exactly same.
The market is really huge for the applications of these radios. That today we will focus more on the GNSS applications, but we have some radios also on the machine automation systems connected to the total stations, to robotic total station between machine and total station. Yeah.
Okay.
The state of the art, this overview for me.
Yes. Okay. Very good. So what the radio modem actually then does in the system. First of all, it enables a half duplex communication. So that's the key thing for the radio, that one radio can be transmitting at one time in the network, and one direction only. Most likely the unit you have inside of your receiver, it's transceiver, so it either transmits or receives, but only one job at the time, so to speak. The unit itself is transparent, which means that that no matter what kind of data you put into the unit itself, it will be transmitted over the air. So radio itself doesn't care if you are transmitting RTCM3 data or some other CMR or anything like that. That is not the radio to choose if that data will be transmitted or not. But big benefit in the radio UHF narrowband radio is that it has a fixed capacity and also predictable transmission delays. So basically everything happens in real time. So in few tens of milliseconds, actually, when starting to transmit data. And the radio itself, it contains two different blocks. So modem logic, taking care of the digital part of the messaging and interfacing to your rover unit itself, and then the radio part taking care of the data transmitter interface. And what happens in radio when you have your base station operating? So the radio modem gets the data packet into the transmit data TD line in the serial interface. And this triggers the transmitter to start up and send the radio synchronization pattern over the air. And after that, it is followed automatically by the data package, which is transmitted. And once your base station radio detects the break in the TD line message, it will automatically return to receiving mode. So therefore, we don't necessarily need anything else but the 3-wire connection for the RS-232 line. In receiving mode, the radio modem is actively all the time listening the channel when you have it powered on. And while it detects the synchronization patterns in the air, it synchronizes it itself to the transmitting data and receives the data from your base station. And basically that is the operation. Very simple, easy to understand, and also in some cases, especially in external radios, it's easy to measure and troubleshoot.
Okay, Marko, I would like to interrupt you just a second because we are receiving the first questions, and in this matter, I would like to remember to all the participants that on the menu on the right side, you have the possibility to write down the questions that you would like to address to Marko or to me. The question is about the radio modem used in transmission. So is that true that after some years of usage, if I use always the same receiver to transmit the data, the internal component that can be damaged, and for this reason should be better to swap base and rover? This is the first question, Marko.
Let's say so that that the radio has been designed basing on and thinking on the fact that it shall work, let's say, several years. We provide 3-year warranty into the unit, but basically the target is that the unit would be operational for, let's say, 10 years, 15 years. And typically, when you are transmitting data and receiving data, everything happens in cycles. So it's very seldom that the unit heats up more than it has been designed for. So I would say that the main challenge in using every time the same unit as the base station would relate to the battery life cycle and battery charging cycles and those type of topics. So radio module itself seldom suffers about this type of activity.
So we have basically we have no limitation to use always the same receiver as a base and the same receiver as a rover.
I don't see that there would be any limitation for that.
Thanks, Marko.
Okay.
Yep.
So then we can carry on with the a kind of a recipe when talking about the working radio link itself. As I mentioned, there are two different interfaces. And when you want to make sure that your external radio works with your rover or your base station, let's say so, this could be a high power radio with the base station itself, you have to make sure that your serial interface parameters between the radio and your GNSS receiver match to each other. So baud rate needs to be the same, number of data bits shall be the same, parity shall be set equally, number of stop bits, and of course the physical interface, which in this case it's RS-232 in most common way. And once you set up these properly, you can be sure that your serial interface is properly connected. From the radio point of view, there are a little bit more parameters to take care, but basically the frequency channel spacing alternatives, they are something that definitely need to match, but also number of data bits, forward error correction or FEC value parameter, and compatibility modes containing the modulations or protocols, how you want to call it. And then there are a couple of more parameters addressing an error check, which are not that relevant in this case, as I have understood that these are not supported by the controller units.
Yeah, most of our users already knows the majority of these parameters because are the parameters that they set up for the communication between base and rover. In this matter, I have another question, Marko. So what is exactly the FAC, the forward error correction, sorry, and when is better to be used? This is another question from one of our participants.
That's an interesting question, and definitely I'm happy to share a bit more details regarding that. So forward error correction, as the name says, it gives you additional reliability into your radio link. So in best cases, you could consider this FEC, having the FEC on, you could consider that it gives you 2 to 3 decibels additional sensitivity into your receiver.
That's not
or
bad.
Into your radio receiver. And therefore, definitely it would be recommended to be used when you want to reach the maximum link distance, and when you operate in, from radio point of view, noisy environment. So if there are some interfering signals available nearby, like for example other radio solutions or other users on additional channels, you might have big engines somewhere and those type of approaches. The challenge, however, or the thing that you need to take into account in these kind of solutions when using the FEC is that it limits a little bit of your throughput. So the throughput might be maybe 25–30% lower than the nominal value you have.
Okay.
But we will come to this topic a little bit later on when I have collected a little table with the different receiver sensitivity numbers and so on. So we can discuss about this further in there, if needed.
Yeah, sure. By the way, very interesting the argument about the additional dB decibel in communication, and the longer link between base and rover with the FAC switched on. This is really, really interesting. Thanks, Marco.
Okay, you're welcome. A couple of images for your reference when you are making or preparing your base stations to operate. So in the modem itself, we have these kind of LEDs, which are actually the indicators of how the radio performs on serial interface level. And they are very useful indicators in that sense that you can see the TD LED in the panel, and every time when you get a message which is coming to the serial interface of the radio modem, you will get the indication for this in red TD LED. And when this radio transmits the signal out from the radio, from the memory block, you can see the indication of red CD LED in there. So basically, when your base station starts transmitting the signal, the correction signal with 1 second interval, you should see these two LEDs flashing basically with 1 hertz interval. And when operating in receiving mode, the CD LED is green when the radio detects the known signal from the radio interface. And receive data RD LED is red when this data is given out from the modem serial interface. So basically, what it means that in rover end, you can check that if that matches to your transmission interval, and also you can figure out that if there is somebody else operating in the area, if you just power up your base station radio and listen the channel before starting to transmit by yourself.
Okay. This is in the case, obviously, we use an external UHF device because just to remind to our participants, with the GMX receivers, we have the possibility to have the UHF hardware inside, embedded into the receiver, or to use through the serial port, we can use the external Satel radio, like the panel which is showing us Marco.
Okay. And then as the troubleshooting tool, if there is a very weak signal or noise on the channel, so when you power up the radio, you can see if the CD LED is lit in orange color. If it's blinking, there is either very weak or unknown signal, or if it's lit permanently, then you can consider that the channel has a continuous interference, and actually the signal level is such high that it exceeds your RSSI threshold value. It's almost like in walkie-talkies you have this squelch solution, so same applies to this RSSI threshold.
In that case, the solution can be to change just the frequency, or we have to change something else?
You might need to change the frequency, or it depends a little bit on the case, and then we can go on the next slide, which actually explains this in a little bit more detail. So when you are willing to understand, and if you are influenced by external noise, or if you are influenced by the let's say, another base station or repeater station which is operating on the same area, you have in external radio, you have a little bit of tools in there. First of all, if the interfering signal is very weak, in the upper right-hand corner, you can see this graph showing our signal and interfering signal. As long as this interfering signal is more than 10 decibels lower than your own signal, you don't suffer about the interference. Basically, you should most of the time be able to operate nicely out on the field. On the modem display, these two different use cases can be seen in a way that if there is a noise on channel, you can see the number on upper left-hand corner of the display. There is a letter N for noise, and then a certain number in decibels, indicating that, okay, this is the noise level the unit detects out on the field. In case it is another radio that is transmitting, you can see the antenna icon and the value after that. This typically is way higher, so way bigger value than this one here. But the background noise typically is somewhere on minus 16 dBm, minus 112 dBm level. So these are two indicators for you that you should be able to operate in there. If your signal strength in this case is somewhere on minus 90 dBm, you should be able to operate properly.
That's good.
In your, or let's put it in other way, if your base station shows that this signal level is minus 100, minus 90 dBm, then I would recommend to change the channel because there is somebody else operating on that frequency.
Okay. We got another nice question, Marco. It's a common question, this one, but I would like that to get your point of view, your answer. So, can the Satel radio inside a GMX unit connect to a radio from a different brand?
In some cases, yes. So basically, there is no such standard that identifies that how the narrowband radio should work. But practically, the manufacturers who who supply this type of radio equipment, they have done some development work for let's say increasing the possibility of let's say cross-brand use, and there might be quite many other brands who are using also Satel radios in their receivers, not only GeoMax.
Yeah, from our experience, I can say that using the Satel radio into our receivers make the life really easier, because the Satel hardware most of the time allows to set up all the parameters that we have seen before between frequency, spacing, channels, but also the protocol that can be really flexible. And in this case, like Marco said, even a Satel radio, if we cannot change the transmission protocol on the second radio, can be set up to transmit or to receive different protocols that are not from Satel. So in this case, once we found the right receipt, between a base and rover to transmit and to receive, and we have all the same parameters, we can say that in 90% of the case we can use a radio from a different brand.
Yes, that is true. Quite often you find the combination of parameters that can be applied for this such system. Yes. A little note on the image I have here on the right-hand side lower corner, just to explain it in a little bit more detail. This case was I have measured from one customer setup where they had actually 2 base stations. You can see the spectrum analyzer image. We are measuring 1 channel, and there was the base station transmitting within 1 second. Oh, sorry, within 1 second interval. You can see this block here, this block here, and this block here. And at the same time, they had another base station operating on the same channel, but the transmission was delayed by half a second. So from this transmission to this spot, there was actually half a second time. And it was located 3 kilometers away from the other one. But they made the system to operate in a way that they had a kind of a time division in the transmissions. So base station 1, 2, 1, 2, and so on, they were transmitting. And at the same time, about the operational factors, that how the radios operate, there was a third transmitter. It could be, for example, a water treatment system or something like that in the area. And it was still using the same channel every now and then, transmitting again lower signal. Mm-hmm. And only operations what we could consider in GNSS point of view, the system was working fine, no problem whatsoever. And depending on the radios, how they operated in this water treatment plant, they might have suffered about some issues. Not necessarily because where this station is located, it might be that our signal at that point would be so much lower that it still works fine. So this is something you have to always think when going on the site and making a quick measurement, that which channel should I use, because the radio environment might be something totally different in, let's say, 5 kilometers away from your area. That is the biggest and the main reason why we always recommend that applying a company license or operating license for safe radio use would be crucial. Mm-hmm. Just to make sure that your system works properly.
Good.
Then a little bit about the range and radio coverage. So there are few factors that have definitely an effect. So major effects have of course the topography, how the landscape is how it looks like. Then what kind of antenna solutions do you use? What kind of TX power you can use, and what are the weather conditions where we're operating. And in this case, first of all, I would say that we are happy, as most of the GNSS systems are working on the 450 megahertz frequency range, which is not so sensitive against air conditioning changes or weather condition changes, or also the signal propagation is not that sensitive than on the higher frequencies. So main methods for us how the signal propagates is the line of sight, from antenna to another. The other alternatives are bending. For example, VHF frequencies, they are more commonly known about and used in maritime because they get longer range in there. Reflections, so whenever you have some obstacles, sharp edges, buildings, anything like that, you might get a reflected signal. And then the diffraction, which in sharp objects actually twist the signals a little bit. Practically, whenever you operate in let's say rural areas, in urban areas, suburban areas, all of these methods most likely apply one way or another. And it's always for the radio. It's radio's job to manage these kind of let's say changes in signal phases and so on. So that's radio design topic. Then I added a little table because always when talking about the range, people are very keen to discuss about wattage. And here in this part, I just wanted to describe that, okay, what kind of a wattage level or transmission power level in watts, and then compare and make a reference that what it means in decibels. And as you can see, if you want to, let's say, double the distance in certain cases, that would mean theoretically you should have a 6 decibels higher signal. In practice, for the salesman, you could say that, okay, 10 decibels is something that doubles the distance. That's a rule of thumb. And another rule of thumb is about the antenna height, that if you lift the antennas up certain meters, as many kilometers you can go horizontally. So if you have antenna masts and have a 5-meter height in antennas, you have 1 watt transmission, approximately you should be able to reach 5 kilometers. Then if you double the transmission power from 1 watts to 10 watts, you should be able to reach 10 kilometers. And then from here you can see from 10 watts up to 35 watts, the difference is 6 decibels. So maybe you should be able to reach 15 to 20 kilometers with that setup. So the main and most efficient way in the systems you can do is the antenna height adjustment. So try to beat the topography, so to speak. And then as we discussed about antenna heights, a couple of examples again. There was a test with a 35 watt radio. On the test site, we ran a simulation basing on that idea, and the customer told us that, okay, they reach 8.5 kilometers in this perfect environment. We ran the simulation with simulating program with a 5-meter antenna height, and from the base station position, which is marked in here, 8.5 kilometers this way and 8.5 kilometers this way, we can see that there is some lack of signals, or the signal level is very low. And basically what happened in this test was that the customers, they actually drove a road which was going this way. And there is a river right here. So their perfect environment was not that perfect, but you couldn't quite see it with a clear eye. So what we did, we made a simulation by lifting the antenna height up to 10 meters and you can see this significant difference in this coverage map. So basically, now you can reach most likely 11-12 kilometers in this area very easily. But this again has a warning that when you are doing the range tests, it heavily depends on the direction you are going. And we have had a habit that if there is a need to prepare such simulations, sometimes we have a network design center service for that purpose. So sometimes if you find a specific area where you want to make some tests and you find some odd results, please contact the GeoMax support team first, and then we can have a chat with Francesco and take a look at what we can do for finding out the solution.
Yeah, really appreciate it.
And as time flies, another approach. So in this case, I wanted to express that, okay, lift the antenna height, get it higher, everything is fine, you get everything working properly. But then there is an other edge of the coin, or other side of the coin, is that if you are going very close to your base station when the antenna mast or antenna installation is very high, what can happen in your system is that is described here on the right hand side. So the rover unit out here works very well when receiving a signal from the base station installed on top of the rooftop of the house. Once you are moving closer to the blockhouse, for example, you are actually putting the antenna signal minimums, you can see here and here, closer to each other, and that way you generate more attenuation between the, or your antenna doesn't work that well. And what might happen is that you are actually moving out from this antenna radiation area. It's not definitely sharp like it has been described here, but that can happen in some cases if you move very close to a highly installed or high installed antenna. Most likely, if you have such high houses there, you would have another house in here, and the signal would actually reflect from that house to your receiver, and it would operate in here. But there are some cases where the antennas are installed into rural areas, into, let's say, metallic masts or very high antenna masts, and then you might not have this possibility in there nearby. So that's also something to discuss and consider when operating.
Okay, we got a new question, Marco. Is there a minimum distance to be kept between a base and rover receivers transmitting at 1, 10 or 35 watts?
Yes, I would say if we think about the worst case scenario and the 35 watt transmission power, the technical fact is that the absolute maximum signal level for that you should put to the rover antenna port is approximately +6 decibels compared to milliwatt. And practical approach, if you have a 35 watt radio, if you are 10-15 meters away from the base station, it should be safe. With these reasonable antennas you are normally using, this whip antenna in the receiver. So if you want to really play it safe, let's say 20 meters, that should be already enough for that.
Okay, good. Thanks.
All right. And then a little bit about the base stations, as we discussed. The normal base station solution, or how would I say normal in that sense, is that I noticed this is the image from the field test we did a few years back, and I was impressed about this base station radio antenna solution. And I was very happy to see that you had something similar visible in this success story in Canada. Was it in Canada? You had this just recently published. So a tripod with a telescopic mast lifting the antenna, providing 5 dBi gain on top of it. And it raises the antenna height to somewhere 5 meters or 6 meters or something like that, relatively easily. And then you have the receiver unit right next to that on a separate tripod. And this is something I would consider ideal mobile base station solution. And I would expect that with a 20 kilometer, with a 35 watt radio, you should be able to reach easily 5 to 20 kilometer distance. This type of setup gave us in that particular test a bit more than 30 kilometers distance. But just wanted to play it a little bit safe in that sense. I guess there is some kind of a limitation that comes in the baseline or into the accuracy when the baseline goes beyond 20 kilometers or so. So
up to 30 kilometers, the accuracy should be always the same. In a nice tolerance.
Yes.
We reach the limit around 30 kilometers, and then the accuracy starts to decrease sensitivity. Okay,
perfect. And then I would say that the normal regular setup with a tripod, that you install the base station with 1 watt radio on the tripod pole like that, maybe giving the antenna height 2-3 meters. You should be able to receive 3 to 8 kilometers with just a regular rover pole. So if you are operating somewhere in between these values, I think the system actually works just fine. And then of course there are alternatives, that having the different type of antenna solutions in this tripod approach.
Yeah,
that is, these are, I would say, the most common approaches for mobile solutions. Okay, and then a little lesson of math for this, just to cover it quickly. So when calculating the battery capacity, the essential information what we need to figure out is the transmission duty cycle. So we need to know how long time does the unit transmit. Is it out of per second or out of an hour? It doesn't matter at this stage, but we need to understand that what we could expect. And in this case, I have made some presumptions. So I have the transmission rate is 1 hertz. Data packet size is approximately 430 bytes, which is roughly 17 satellites you are transmitting. And the data rate is 9600, which could be then Satel 4 FSK, 12.5 kilohertz, and forward error correction off. So basically the nominal data rate. And the transmission power is the full power the external radio can provide. So this gives us the duty cycle, which is approximately 45%. And it should be less than 50% if you want to use a repeater station in the system. Otherwise, you can increase it. And then we calculate the transmission time for one data package. Simple math, we take message length in bytes, number of bits per byte, which is 10 bits in this calculation, and it's divided by the data speed. And we get that, okay, transmission time is roughly 450 milliseconds out of 1 second. And here you can see actually that the maximum message length is 1 kilobyte, which is the size of the data buffer we have inside of the radio modem. So if you have a repeater case, this is definitely a maximum data size package. Okay, so then now we know the transmission time and we know the duty cycle. Yes, Francisco, did you have a question?
No, sorry.
Okay. Yes. So we know the transmission duty cycle, 45% out of time, our unit consumes the maximum power it can, which means that it's 54 watts. 55% of the time it's in receiving mode, giving us approximately 1 watt consumption. And then these values, they change. So I have listed different power levels and different power consumptions into this table in here. But basic approach with full power, this is how it goes. From average power consumption, we then can calculate the average current. So transmitting power, receiving power divided with the voltage we have in the battery, it gives us the ampere numbers.
Ampere.
And then total energy consumption for 8 hours, we multiply the average current by time in hours, so we get 37 ampere hours. This is how much energy we would need for operating 8 hours out in the field. And then if we go further, for different working times, I have listed or made a table, so different power levels on this column here, and different working times on these columns here, and then ampere hours as the result. So 37 ampere hours, 8 hours with full power. 55 ampere hours, full power, 12 hours. So this is basically the calculation. And then we come to the battery capacity or topic. If we have a lead acid battery where we're supposed to have 70% of capacity left when we finish, we get the working or the ampere hours that the battery should have 122 ampere hours roughly in as the capacity for operating. Then there's the question, do we need a continuous transmission who really works 8 hours without stopping the base station at all? Or do we have the charging opportunities during the operations and so on? But with very basic calculation, we can figure out this capacity part. "120 ampere hours, it sounds like a relatively big battery. In diesel car, I think you have something like that. And the basic idea then is that how can we use a smaller battery? So of course, then the key thing is that transmit as shortly as possible. So what can we do for maximizing this operating time? And then we come on to the topics over the air data rate. So should we use select or choose as efficient modulation as possible, use as wide channel width as possible, so that you can get maximum data rate. Then alternatives are that can you adjust the transmission interval, so maybe from increasing it from 1 second to 2 seconds, so you transmit only every 2 seconds to save power, or use the lowest possible power level, or then as the last option in this case, do you have an opportunity to lower the number of satellites that are tracked, or choose the efficient system protocols? What is the most efficient protocol you can choose? So just sending the shorter data packages, and then we can carry on with the protocol examples. So just a table describing Satel protocols, forward error correction off or on, and what is the efficient data speed with these protocols here, and what is the sensitivity level of the radio, to understand that, okay, what kind of range can I expect without losing the capacity, or vice versa. Note on the GMSK based part here that the data rates given in here are nominal data rates. Nominal meaning in this case that, for example, in backrest GMSK option, the forward error correction typically is on, which means that this value shall be reduced a little bit, maybe 20, 25, 30%. But at that case, you can also notice from receiver sensitivity that you can reach most likely a little bit longer distances with this. Yeah. As the conclusion from this slide, without reading that much of additional things, typically 4FSK is used when the high power radios are used in out on the field. I would recommend, if you have a pair of Zenit 40 units and a lot of satellites, basically you don't lose in range, other if you consider the power level, or if you exclude the power level thinking, you don't lose the range, but you have basically a 50% higher data capacity in use. And then if you want to carry on and get a maximum range, but you want to sacrifice a little bit in your data capacity, then you can choose the GMSK options in your system. But it's more like fine-tuning in that sense. Always when trying to reach the maximum range, I would say that use forward error correction on, because that gives you the best receiving performance that a certain modulation or protocol can provide.
Basically, the variables in this case are the size of the data that we are sending out. And in this case, if we are using receivers that are able to track only GSM and GPS and GLONASS, for example, or when we use the full 4 constellation, GPS, GLONASS, Beidou, and Galileo, and the range that we want to achieve. But in this case, the FAC can help us in the choice.
Yes, that's correct. Okay, and then if we come back to the battery capacity calculations, now if we change, we keep everything else as it was, data packet size equal data rate is something we change the protocol and make the calculation, and what we can actually see is that the transmission time for one package, it basically it drops to somewhere close to 23%. And the numbers change accordingly, of course, and here we can see a significant change. So divided by 2, natural thing is that we are close to half of the consumption what we will achieve. And again, a comparison between battery capacities. 45% duty cycle, what kind of a battery you need, and then by simply changing the protocol, you can achieve smaller battery sizes. Again, if you decide that, okay, let's transmit only once per 2 seconds, you could divide it by 2 and so on and so on. Very simple math.
Very simple, but really interesting how much the battery consumption change, just changing the transmission protocol, just choosing a most efficient transmission protocol. This is really impressive.
Yes, and the other thing which actually, if I may go back a few slides into the slide where I had these decibel values.
Yes, sure.
Now when we have a look at this, that we are on 64 ampere hours, and here we have 42 ampere hours or 48 ampere hours, and let's go in here. 20 watts is plus 43 dBm. It's only 2 decibels lower than our maximum. And if you have 1 decibel difference out on the field, you can't actually measure it. You need a practically calibrated equipment to detect it, and 2 decibels, it's typically the signal variation. So the real benefit that you get from 35 watts transmission power compared to 20 watts, for example, is in the distance is not that much. But in here, in this part, you can actually see that the battery capacity might be 1/3 that you need.
Yeah,
that is something which starts to play a role in here.
That's impressive, Marko. Really.
So I think if there are any further questions, I'd be more than happy to answer them. This is pretty much I had in mind to share with you today. And is there something further we shall discuss?
So is there another very interesting question, Marko? So what is the relation between channel width and data speed? Channel width and data speed. Yeah.
Okay, let's go back in here. So here you can see channel width 12.5, 25 kilohertz, and then the radio data speed 9,600 or 19,200. So the difference comes from the typically when the wider the operating channel is, the higher capacity you get. And of course we want to transmit the maximum data rate what we can on this channel width on 25 kilohertz channel by not sacrificing anyway for example the ETSI regulations of the radios. So that is the on 12.5 kilohertz. Typically the radio sensitivity is a little bit better, But then on wider channel, we can then provide you more data speed in there. So the higher the channel width, the higher the data rate. And then we also have these options about the higher modulation rates as well.
Good. So let me check. Just if you have some more questions. So okay. So anyway, the video of this webinar will be available by the end of the webinar itself. So I would like to thank Marko for your participation, for all the information that you gave us today. I really appreciate, and I'm sure that also the participant appreciate a lot. This was the first webinar made as a live interview. We will have in 2 weeks another live interview with Kevin Corazza. Is the software engineer that has programmed our suite of software XPAD just in 2 weeks. So I would like to thank all of you for the participation, and so for any questions that you would like to address to us, please do it at academy@gmxpositioning.com. We will a pleasure to reply. Marko, thank you very much again. I hope to invite you again in future for another very interesting session like this.
Okay, thank you very much on my behalf and on Satel behalf. It really was a pleasure, and I hope that helps you in the future cases. And if there are any questions later on, Francesco, you know where you can find me.
Yeah, sure. I will never forget.
Okay.
Thanks a lot, Marko, again. See
Thank you very much. Bye-bye.
Thanks for watching.